You've been struggling with AISC interaction equations for beam columns. This is the correct video for you. In this problem, we're going to look at a W14 by 132 beam subjected both to end moments and an axial load and see whether the member satisfies the AISC interaction equation. Now, to begin this problem, we're going to look at the loads that we have. We have both the X and the Y axis loaded with dead and live loads in both axes, and then we have a point load or an axial load of 125 kips in the axial direction of dead load and 300 kips of axial load in the live compressive direction. So with this information, we should also note that we have a 25-foot column and it is pinned at both ends in all directions. So we have almost everything we need here, really. And also for this problem, just for the purposes of this, for you to understand how the interaction equations are going to work, we're going to assume that the moments do not need to be amplified, which simplifies this problem drastically. So what we're going to do first is we need to go through and factor all these loads. So for this problem, we are using LRFD, which means since we only have a dead and a live load, we know which is going to govern. It is going to be case 2, 1.2 dead plus 1.6 live. Let's do our point loads first. We have 1.2 times 125 plus 1.6 times 300. And this will give us our PU, or our factored load. And this is going to be 1.2 times 125 plus 1.6 times 300 is equal to 495 kips. And this is equal to PU. Now with this information, we can go and we can look at the first part of this equation. And what it's going to say, we're following AISC equation H1-1 parts A and B. It's determined on whether we're going to look at this. PR over PC has to be less than or equal to greater than 0.2 is going to give us one equation, or PR over PC is going to be greater than 0.2, in which case we use a separate equation. So when you actually break this down, we're using LRFD, so what we're saying is PU over PC PN has to be greater than or equal to 0.2, or PU over VC PN has to be greater than 0.2. It's going to be one of those two cases. So PU we already found. We found PU is equal to 495. And to find VC-PN, we can go to table 6-1. And with table 6-1, we can go to 14 by 132. We can say we have a 25-foot length, and we're going to have to interpolate here because the table does not have a value for 25. It has a value for 24 and for 26 feet. Those values are 1140 and 1060. So we can just average them because it's right in the middle. We would have to actually interpolate if it was not a value directly in the middle, but it is. And we're going to get 1100 kips of axial strength. 14 132s are pretty strong columns. So we can just double check this again, 1140, 1060. Yep, that's exactly what it will give us. So 495 over 1100, we know is going to be greater than or equal to 0.2, right? It comes out to exactly, let's see, 0.45. So yes, 0.5 is greater than 0.2, which means we are going to use H1-1A, which is PR over PC plus 8/9 times MRX over MCX plus MRY over MCY. And let's rewrite this for LRFD. So this is going to be PU over VCPN plus 8/9 times MUX plus, this would be VBNNX plus MUY, phi B, M, N, Y. And that's pretty much all we have to do. Oh, and also, these have to be less than or equal to 1.0. And this is what's going to determine whether the member is adequate for as a beam column for both types of loading. So, phi U over phi, or PU over phi CPN, we've already found that's 0.545. However, when we get over to MUX and MUY, we know we need to start factoring. So we have these numbers up here. I'll just do the calculations up here. We have, if we combine these loads in the x direction, we have 1.2 times 100 plus 300 times 1.6. We're going to get 600 equals MUX. And MUY is going to be 1.2 times 35 plus 1.6 times 68. We get 150.8. So 150.8 and 600. Phi B, M, and X can also be taken from table 6-1. We're going to have to interpolate yet again. We're between 795 and 779 here. So 795 plus 779 divided by 2. Be careful with your parentheses on this. You can always catch up. We have 787. Ooh. 787, and CB is not a factor here, so we're going to say it's equal to 1.0. We have an applied moment at the ends. We do not have, we have an applied and uniform moment. We don't have any sort of uniform loading situation. MUY was 150.8, and we can go to the table. It's not going to depend. This will be on the table in the lower left corner. It's not going to depend on the length of the member because the weak axis bending strength is calculated differently. But that's a discussion for a separate video. So we have everything we need here. Now we can go in, we can plug in the situation. And we need to get a value less than or equal to 0.1. We have 0.45 plus 8 divided by 9 times the quantity 600 divided by 787 plus 150.8 divided by 424. And we get a value that is quite high. We have 1.4438. This is greater than or equal to the member, or the value of the member. So this member is actually not adequate for this loading situation. One important thing to notice about how this equation actually works is we're reducing the value of these moments as a function of this ratio of the required strength being so high relative to the required strength being so high relative to the available strength. And part of what that is if you think about what a moment does, when we have a member that's in loading and there's a moment load, say we have something like this, we have compression on this side and tension on the other. Well, the bending strength actually helps compensate for some of this tension, or I should take that back. The axial load helps compensate for some of this tension. And because of that, we have a trade-off here where we can now reduce this factor. So that's essentially what this equation is saying. And we can look briefly at what H1-1B is, just so that you know. So this is if PC is less than 0.2. In other words, very low ratio of required strength to needed strength, or PU to phi CPN in this equation because we're using LRFD. Then you have PR over 2PC plus MRX over MCX plus MRY MCY, and then still less than or equal to 1.0. So that's how you would go about it if you had a different ratio here. We could have easily created that problem where all we would have to do is create a smaller axial load than what I had written out here, and it would have been possible that it passed that, but that's not what we had in this case. So in this case, our member is not adequate as a beam column. So you can take this method and apply it to pretty much any beam column problem. Well, that's not true, actually. If you're told specifically to ignore moment amplification, this is how you go about the problem. We'll cover moment amplification in a different video and how you use that to get a different MU factor. But until then, I hope you found this helpful, and if you did, please drop a like and subscribe to the channel, and we'll see you in the next one.